Hello, ladies and gentlemen, good to see you again. Today we're going to be going over the 11th laboratory session, and we're going to be focusing on linear regression. So I hope you'll be able to download the code from Blackboard and open it up within your R script. First of all, what we need to do is we need to acquire the data, and we're going to be using data that actually comes from Lattice. So Lattice is a graphics package that I mentioned before, which I have used quite a long time ago. I don't use it too much anymore, but it does provide some inbuilt data sets, which are pretty handy, like many other packages do in R, so that's worthwhile. So require the Lattice data package, and then when you actually open it up, you can assign the variables of interest from environmental. So let's just have a look at this data set first so you know exactly what we're looking at. And environmental is a set of environmental data, atmospheric environmental data for New York City. So essentially these are daily measurements of ozone concentration, wind speed, temperature and solar radiation, which have been taken with NYC from May to September 1973. So the data is quite dated now, but this is one of those classic data sets which is very good for having inbuilt within the code because they don't take up too much space within a package, but then also people kind of are familiar with them, so you get fairly standard usage of some of these packages to show reproducible examples, for example. So this is a good one. There's also the sepal plant leaf width, which is another famous one which is used a lot in ggplot2. So anyway, the point is within this data set we have ozone measurements, and these are the average ozone concentration hourly in parts per billion. And we have radiation, so solar radiation from 8 to 12 in Langley's, so I assume that's 8 a.m. till 12 p.m. in Langley's, temperature, maximum daily temperature in degrees Fahrenheit, and wind, so the average wind speed between 7 a.m. and 10 a.m. in miles per hour. So what we can do is we can assign those two variables of interest to us, so x and y, temperature and ozone, to x and y for us to actually understand the influence the temperature may have on ozone concentration. So just before we begin, ozone is a sub-byproduct produced in greater quantities as a result of, for example, internal combustion engines. So if you're driving your car, you'll be releasing lots of nitrogen dioxides, and that may lead to the production of ozone because it can combine with other molecules and produce something which is actually potentially quite harmful to you if you're on the ground breathing in these ozone particles. So that's the kind of background to this. We're interested in understanding how temperature might affect ozone concentration. So on the x-axis here we have temperature in degrees Fahrenheit, and on the y-axis we have the parts per billion of ozone within the atmosphere, all within NYC. So what we can do first is we can find the A and the B values. So A being, let me just bring up the slide so that you're fully up to date with where we are. Yeah, so this is a good example. So what we want here is the intercept, so the alpha value, and the slope value, which is the beta coefficient B. So what we're going to do here is calculate B first, and then we're going to calculate A, okay? So let me just find the correct slide where we went over, so this is the version that we're using here. That's correct. So what we're doing is we're finding the correlation coefficient between x and y here, and then we're multiplying it by the standard deviation of y over x, and that helps us obtain the beta coefficient, which is 2.43, using this rather simpler equation than the previous one which I showed you, which we're going to avoid in this case. And then we're going to find the alpha value, So essentially what we're doing is we're taking the mean of y and we're subtracting the beta coefficient multiplied by the mean of x, okay? So we're now finding this left-hand equation over here. And when we do that, we get minus 147.6 for our intercept value. And we can actually plot this line on the plot that we've already produced over here. So we've now got our line of best fit. So let's just have a look at abline very quickly so you know what's happening here. So essentially, using abline, we can add a straight line to a plot. And this function adds this plot by using the intercept and the slope, which we provide as single values. So that's what we've done here. We provided the A value and the B value, so the alpha and the beta value for the regression that we've already manually calculated by hand. And that allows us to produce the line of best fit like this. Okay. Then what we want to do is we want to test the coefficient of determination to see how much of the variation depends on the explained component. So let's first just take the number of samples and then let's obtain the regression sum of squares. So the RSS value here is quite large. And then let's obtain the total sum of the squares. So let's just find these equations. Here we go. So we've got the RSS and the TSS, and then when we find, when we basically obtain the coefficient determination, the R squared value, what we're doing here is we're dividing the total explainable variation within the data set, so the regression sum of squares, by the total variation that we have, the total sum of squares. So it's the explainable amount over the total variation. And that gives us an R squared value of 0.48796. Okay, and once we've got that R squared value, we're able to then calculate our F statistic. Okay, so we can use the F statistic from Hanover expressed in terms of R. So you can see in the book, actually, if you want to, equation 17.5, which I just have here. So apologies, I just had to find the equation within the book. But as I said, it was equation 17.5. So I've actually written in the code here the equation numbers or the page for where you can find the equations in order for you to follow through with chapter 17 in the book for how we calculate this. So essentially we're able to get the coefficient of determination, then calculate the F statistic using that equation that I just mentioned. So what we're doing is we're taking the R squared value and multiplying it by n minus 2, so number of degrees of freedom to get the numerator, and then we're dividing it by 1 minus the R squared value, and that's giving us an F statistic of 103.874. So the number of explanatory variables that we've got, so it is 1, so df1, degrees of freedom 1. And the number of parameters in the regression equation here, which is df2, so n minus 2, then allows us to basically use the pf function for the F distribution to provide it with a quantile, as we do down here, and it provides us with a probability in return for that value that we've produced for F, which based on those 2 degrees of freedom, those 2 degrees of freedom values that we provided, is incredibly small. So it's 1.55 to e to the minus 17, so highly significant impact there. So essentially what we've done is we've calculated the alpha and the beta coefficients after plotting the data, and then we worked our way through to get the F statistic by obtaining the regression sum of squares, the total sum of squares, and the R squared value. And then what we've done is we've just used the fairly normal quantile-based approach to obtain a probability for the value that we obtain for the test statistic, which here is based on the F distribution. So that's how we calculate by hand a regression-based approach. So it's a bivariate regression-based approach. So we've used two metrics. So we've used a predictor variable and an output variable. So temperature being the predictor variable and ozone being the outcome variable of interest. So essentially, from understanding this, as the temperature increases, the amount of ozone in the air, the parts per billion, increases as well, and therefore you may be more exposed to harmful ozone particles in the air as the temperature increases, for a variety of reasons. Okay. So what do we do when we want to understand this just using a more simple function-based approach? Well, always start as ever by plotting your x and your y data. So this is exactly the same approach that we took before, the same data variables. It's just that now we're using the inbuilt linear model that's provided by R. So if I type in LM, we look at the help, this LM function is allows you to fit linear models, so can be used to carry out regression, single stratum analysis of variance, analysis of covariance, etc. But today we're using this for a regression-based approach. Okay. So when we do that and we print to the console the regression output from the model, what it's saying is you specified a formula which is y as the dependent variable and x as the explanatory variable, and it's estimated an intercept value of -147 and a beta coefficient of 2.4. That doesn't provide us with all of the output though, so what I've done is I've just printed the summary, which provides you with all of the elements of the model essentially. So what it's saying is exactly what I mentioned before for the formula specification, but then it also provides now the residual statistical distribution, which we spoke about at length in the lecture, and I explained that what we're really looking for here is to understand whether the distribution of the residuals are potentially normally distributed. There's quite some significant movement in the residuals here, which are raising some issues for me. So if this was a project or a dissertation or a paper, I would be concerned with actually trying to use a normality test in order to assess that they meet the normality assumption. So that could be the Kolmogorov-Smirnov test, for example. So that's something which you should look out for. Then we've got the coefficients for the intercept value and also the x value, and we discussed this at length. So we've got the intercept of -147 here, but importantly we've got this predicted this coefficient for the x value, which is 2.43. So for one increase in the x value, which is so for one increase in the predictor, which is temperature, we could have an increase in the y value of 2.4391, which is the proportion of the ozone in parts per billion. So essentially, that's the approach. Apologies, someone just came to my door to deliver a parcel, so I do apologise. So hopefully that's clear to you now. You know, I tried to drill home in the lecture that we need to think about this as a 1 unit increase in the predictor leading to a certain increase in the y variable. So down here, I basically place this little red dotted line, because here what we're saying is there's a 1 unit increase in the x, and that leads to a certain increase in the y variable here, so the slope. Okay, so I hope that that's clear now. And then the important point is that that's the estimated coefficient. We then have the standard error, which is very small for our x coefficient, for our x variable. And then we have a t-value of 10. So basically, if you divided the coefficient by the standard error, you would get a t-value of 10.192, and that would be equivalent to this very small p-value, which is 2 to the e to the minus 16. So it's highly, highly significant. So we can be, more than 99% certain that this variable has a significant impact on the outcome variable. Okay. So hopefully that's provided you with some good insight for how we run this function and obtain those coefficients that we're interested in, including their p-values. We also end up with the model statistical outputs as well. So the adjusted R-squared value here, it's pretty similar to the regular R-squared value. It's about 48% of the variance in the output variable that's explained by this one independent variable x that we have. And that leads to an F statistic of about 103.9, which was, if I recall correctly, the same F statistic that we produced when we manually calculated these statistics for this particular approach. Okay, so I think that that's good. It nicely ties together, and we've got a highly significant p-value for the model overall. Okay, so let's now just add the line of best fit to those to the scatter plot, and you can see that this is what we've just fitted. We do want to view the residuals, so we can do that by using the residuals function. And when we do that, what we do is we're extracting the model residuals from that LM linear model function that we used in R. So the residuals is a generic function to extract the model residuals from objects returned by modeling functions. Okay, so I hope that that's fairly straightforward to you. Here it's just printing to the console that you can just allocate it to a variable if you want, and then you can just treat it as a normal data object that you might have as a vector, for example. Okay, and we can also view the standardized residuals using R standard. So when we get the standardized regression residuals, what we're doing here is we are taking the normal residuals. Let me go to the slide where we've got this. Residual analysis. Here we go. Normal residuals. So we're taking the normal residuals and we're basically standardizing them against the number of variables that we have. So we're getting the residual standard error essentially. So this is a way for us to standardize those outputs. And here again, I'm just printing them to the console. You can see generally that they're all between, +2 and -2, maybe a couple of outliers that we've got. And you could just treat that as you normally would. Okay, so you need to go through all of those residuals and check that they meet the assumptions. And we'll do that in a second, but I just wanted to quickly show you how we would do a prediction, because I mentioned before, this is one of the most fantastic things that you can do with these types of statistical models. And the application of this is endless, and if you know how to command this statistical technique, you can command a much higher salary, or you can command better job working conditions. And I've worked in a range of different places, and even if you're all on the same, being the person who can do these stats in a team where many other people can't makes you invaluable, and therefore you're more likely to always be kind of kept and wanted, and that's just generally what you want when you move into a workplace. So I can't emphasize enough that you should try to do some work on this within your future kind of research career at GMU. If you do a dissertation, for example, you've got the code here. Now you just need to collect some data for your own topic and try and apply these methods. So if you're looking for a dissertation supervisor and you want to work on this, do reach out to me. Okay, so how do we actually do that? Well, what we're doing is we're saying we're taking a new value of the x variable, so the predictor variable, let's just say it's 90 degrees Fahrenheit. And then what we're going to do is we're going to use the alpha intercept value that we've already estimated. We're going to use the slope that we've already estimated, but we're just going to plug it into that equation that we have. Y, so the output variable, is equal to the intercept plus the slope multiplied by the x value. Okay, and that's what we're doing here. So we're getting a y hat value of 71.87382 parts per billion of ozone. Okay. So you can also use this predict function. I mean, we had got that value already just by running through this this equation just here. I think one of the benefits maybe of using predict is that you can actually provide it. It might be easier to provide it with a longer list of values. So it's a generic function for prediction from the results of various model fitting functions. The function invokes particular methods which depend on the class of the first argument. Okay, great. So I think that that's really exciting. Do take regression models that you fit in and try to do forecasting prediction, particularly if it's something which might happen in the future. So like say you're going to try and predict when the first frost is going to be next season based on data you've collected, you can actually get to that next season point and evaluate how good your model was. And that's always fun. Okay, great. So that's how you do the prediction part. Now let's focus just quickly on the residuals. So I just wanted to emphasize that the residuals, if you remember correctly, it's equal to the observed response minus the predicted response, okay? So it essentially shows the deviation from the regression line. So let me find you a good example of this. So those residuals are, if we have a y value on the y-axis and the x value on the x-axis, we have a bunch of data points, 1, 2, 3, 4, 5, 6, 7. The residual is that distance between the line of best fit that we fitted and the data point. So D1 is this distance here. D2, the second residual is this distance here. D3 is this distance here, and D4 and so on and so forth are the distances from the line to the data point that we have. Okay. And the point of kind of assessing this is that we need to be able to see if there's any violation of the model assumptions regarding the residuals, which we covered in some depth. So let me just pull out that slide where we cover this, which is here. And that's because we have all of these requirements that we need to meet about the residuals within those assumptions for the standard regression approach. Okay. We're looking for linearity and equal variance. We're looking for independence. We're looking for normally distributed residuals. Okay, so how do we do that? Well, let's just plot those fitted values against the residuals. So we've got the residuals on the y-axis and the fitted residuals on the x-axis, and they look reasonably randomly distributed there. I mean, it would be nicer if we had more of a spread, but I don't think they're causing any alarm bells for me here. There doesn't seem to be any discernible pattern, so I think that would be okay. Then if we were to plot the fitted against the standardized residuals, all that's changed here is that we've changed the value on the y-axis. So sorry, before what we had was the absolute value, whereas now what we've done is we've plotted the standardized residuals. We do have quite a skew in the data, so it's pushing up to 5 standard deviations away, and I think that's quite a large amount. So I think we would need to seriously consider the assumptions for this data that we're testing. And then finally, we can plot the standardized residuals. And what we're doing is we're plotting it against an index which represents the typical distance separating a point from the regression line. So it's the standard residual standard error, essentially. Okay, so we did cover this within the lecture. Here we go, for how we calculate this particular index. So that's what we get here, and these now are much more sensibly. I think that these look, I'm very happy with how these are distributed here. Quite randomly distributed. So we can add the line we can add the mean line to the residual plot just there if we want to evaluate them. Okay, finally what we need to do is we need to look at the level of normality of the residuals based on the kind of quantile plot that I mentioned before within the lecture that we went over. So we're doing a QQ plot. We're comparing the theoretical residual quantiles with the actual. And deviations from the line imply a lack of normality. So it's quite bad here because you're in this example where it's not very good, you're coming off the line at both the bottom and the top of the residuals, and then in the middle you're dipping below, so it was suggesting it was slightly skewed to the left. Here we have the same kind of a diversion from the line, but it's kind of at these tails. Actually, in the middle of the distribution, these actually look quite normally distributed. So I think that these look okay, but I think that I would probably need to test these with a formal test just to be entirely sure that we do definitely have normally distributed residuals. Okay, so that's how we basically check the residuals, do the residual diagnostic. You've got the code here now, and we've been over it in the lecture, so I hope that you'll be able to digest this information, think about how you can apply it. So let's think about multiple regression. So how do we now add in more explanatory variables? So before we were focusing on bivariate regression, so we have a predictor and one explanatory variable. What about multiple regression, where we have a single predictor, but then we have maybe 3 different explanatory variables? And that's what we're doing here. So we're using all of the environmental data set. So we're focusing on the ozone concentration as the dependent variable, the temperature as the first predictor explanatory variable, at the level of solar radiation as the second predictor variable, and the wind level as the third predictor variable. So let's start with a plot of all of these, and let's just, for simplicity, let's just take the lower panel, okay, for all of these metrics. So what we have here on the y-axis is the ozone concentration, so from 0 to 150 parts per billion. And then for radiation, we have the radiation metric. So let me just... here we go. So I just want to go back to make sure we've got the units correctly. So the solar radiation is in Langleys, so from 0 to 300 Langleys. And we can see that there's a marginally positive correlation there. So it appears that as the radiation level increases, the ozone level increases as well, ozone concentration. And then when we move to temperature, so this we know already is on the x-axis, it's Fahrenheit, degrees Fahrenheit, so from about 60 degrees Fahrenheit all the way up to over 90 degrees Fahrenheit. And that's got a much stronger positive correlation, I think. They seem to be kind of, once you pass 75 degrees Fahrenheit, it seems to really pick up quite strongly and increase the ozone level then. Maybe because of humidity, obviously, particularly around New York. in the summer times, it starts to get hot, it gets humid, and that traps a lot of pollutants in the air, and that might cause more ozone to be produced as a consequence, particularly when combined with UV. And then for wind, what we have here, again on the y-axis we have the ozone, but then on the x-axis we have miles per hour of the wind speed. Okay, so what we have here is a negative correlation, negative linear correlation. So for as the wind speed increases, the concentration of the ozone decreases. Okay, so that's quite a nice. That's running in a different direction to the other variables. And ultimately, as the wind increases, it's able to blow more of the Pollutants produced by the congestion of carbon-based, fossil fuel-based combustion engines in New York City. It's able to blow that across, so you're getting fresh air potentially coming in maybe from the eastern seaboard, and that lowers the concentration overall of ozone. So that's the type of panel plot which you'll want to do if you've got lots of variables and you want to understand how maybe they all relate to each other. So definitely think about doing this as your first step when you're starting out on a multiple regression problem. Try and understand how the data are related to each other. Okay, so I think that's fairly straightforward. Now let's actually specify our multiple regression equation. So what we're doing here is we're saying we think that the ozone is the dependent variable, and that temperature, solar radiation, so the amount of sunlight, and wind speed are going to be good predictors of ozone. So let's run that, and we can see that we've had that equation specified within the linear model function. Ozone is our dependent. You see the tilde is basically the equal sign in this case. And then we have the predictor variables, which is temperature plus radiation plus wind here on the right-hand side of the equation. And then we have coefficients for each of these. Okay, and we can actually get a summary of that. And don't be intimidated by what we're getting from the console here. This is just exactly the same as what you saw in the previous bivariate laboratory. So what we've got is the specification of the equation, and then we have the residuals. So this is the statistical distribution of the residuals. So we've got the minimum, the maximum value, and then we've got the median and the quartile values for the first and the third quartiles. And these are seem a bit skewed. So I'm looking at the difference between the max and the min, and then the Q1, the Q3 values, and there's quite a bit of movement there. And the median obviously isn't the same as the mean. We would expect the mean and the median, sorry, to be 0 if they were perfectly distributed. So this is giving us an indication that maybe we've got slightly skewed data here. Okay, so let's interpret the coefficients. So it's the same structure as the previous regression coefficient outputs. So we've got the variables as the rows, so the intercept, the alpha, and then we've got our beta 1 value temperature, our beta 2 value radiation, beta 3 value, which is wind. And then we've got the estimated coefficient. So we think for a 1 unit increase in temperature, it leads to a 1.65121 increase in the parts per billion of ozone in New York City. And then we think for a 1 unit increase in solar radiation, so the UV level, we get a 0.05980 increase in the parts per billion of ozone. And then likewise, as we increase the wind speed by 1 mile per hour, we get a reduction of 3.3760 parts per billion in ozone. So obviously there's a negative correlation there. And the standard errors are all really quite small if you were to divide these by, so the coefficient by the standard error, and you would get these t-test statistic values over here. So 6.5, 2.5, minus 5.1. And we have highly significant values for temperature and for wind. At the 99% level, we can be certain that this just hasn't occurred by random. And then we have significant value for solar radiation, although it's quite a lot smaller. So it is below the 0.05 significance level that we would expect if we wanted to be 95% certain. And it's actually still a very small coefficient. It's just that the other values were so incredibly small. It seems like it's less significant. So there we have the standard coefficients, and how much variation does the model explain? Well, the standard R squared is about 60.6%. 60.6% of the variation in the Y variable is explained by those 3 X beta coefficients. So there's those 3 variables that we use as explanatory metrics. And the adjusted R squared values, when we take into account the fact that we've added more variables in, and that can inflate the explanation sometimes, it's about 59.5% of the data variance that's being explained. So that gives us an overall model test statistic of about 54.91, which is highly significant. So this is a pretty good model. I think if I was taking this further as my research, then I would want to go and look and use formalized tests to check that those residuals are meeting the assumptions that we need in order for this to be an appropriate method. Okay, so that gives us a good summary of those outputs. We can also visualize the standardized plots. So this is plotting temperature against the standardized residuals. We can also plot the radiation level, so solar radiation level against the standardized residuals. So these are all looking quite nice actually. And then we can plot the wind as well. So maybe a little bit of nonlinear variance there, so a little bit of heteroscedasticity, so we might want to check some of these, but some of them looked okay. And we can also look at the fitted values. So we have fitted values here for the actual model that we would want to explore. These are harder to visualize though when we've got more than one independent variable, so it's no longer a single line of best fit essentially. And we can also check using QQ plot, so we can fit the standardized residuals to using the QQ plot, and then we can add the actual quantile plot line of best fit here. So we can see that the variables in the middle of the distribution are reasonably normally distributed, but then we have quite a lot of noise down here in the lower and the upper ends of the distribution, which would be concerning to us. Okay, great. So that is the final laboratory of the term, and I hope that this has provided you with a good overview of how we carry out bivariate and then multivariate regression. This is such an important technique, so please put a strong emphasis on learning this. It will come up in the exam, and make sure that you have a good understanding of it. Particularly as it can help you out so much in your future career. Okay, so I will place the assignment up on my Mason, and reach out to me if you've got any further questions, and if not, then good luck with the remaining assignments, good luck with the exam, and please reach out to me if you've got any further questions. As I said before, I'm slightly going to change the marking criteria to better reflect some of the things that have gone on this term. You know, it's been harder for us to engage, and I think that might have hit your kind of understanding and learning a little bit, so I'm going to adjust the marking criteria. The other thing I'd like you to do, please, is you should have received the course feedback, which is super important because I'm measured based on the course feedback which you give there, so I'd really appreciate it if you filled it out, please. You know, if I get no feedback, that's kind of bad for my own progression. It's also bad for future people who take the course, because I use that feedback to improve. And as you know, this has been my first time teaching this term at GMU, which I've been really excited about, but I'm really keen to improve the course and make it easier for people in the future to kind of get a grasp of these key techniques. So please do fill out that course feedback, which you should have had emailed to you from the College of Science to your email inbox. So please do that. Okay, fantastic. Well, thank you very much, ladies and gentlemen. It's nice to see you, and hopefully we'll all be back on campus soon enough. We can do this all in person. So thank you very much, and I'll see you all soon. Goodbye.